Continuing on physical chemistry, chapter 12, we're starting section 4 now. We're going to talk about the fourth colligative property now, which is osmotic pressure. So let's say we have this system. We've got a membrane down the middle that only A, our solvent, can go through. On the left side we have pure A, so it has chemical potential mu A star. And then we have a certain pressure here, pressure on the left side. Over here we have solutions. We have A and B. It's a two-component system. So the A over here has got chemical potential just mu A. And then if there's a certain pressure here, that's pressure on the right side. We're starting out initially with these two levels the same, and the pressure is equal to the same. Now, let's see here. Also, this membrane is thermally conductive, so they're in thermal equilibrium also. Now, we know that mu A star is going to be greater than mu A, because A is going to spontaneously flow from left to the right, and the liquid level here is actually going to rise. This one will go down. So we know on the left side we have mu A star, and it's got to be greater than mu A on the right. Continuing on physical chemistry, chapter 12, we're in section 4. So remember, the derivative of the chemical potential of A with respect to pressure holding temperature constant is just equal to the partial molar volume of A. And remember, A is our solvent. Now also we know from way back chapter 2, the differential of Gibbs free energy is equal to minus the entropy times the differential of temperature plus volume times the differential of pressure. We're going to be holding temperature constant, so this whole term goes to 0. So that would just give us dG is equal to VdP. Now we know the partial molar volume of A is going to be greater than 0. And we know that the change in the chemical potential of A is going to be greater than 0. Therefore, the derivative of pressure is going to be greater than 0. Now let P equal the equilibrium pressure on the left side, and P plus pi be the equilibrium pressure on the right side. That means pi is the extra pressure that we would apply to the right side in order to make the chemical potential of A on the left side equal to chemical potential of A on the right side. Now we call pi the osmotic pressure. And of course at equilibrium we know that the chemical potential of A on the left has to equal the chemical potential of A on the right. Continuing on physical chemistry, chapter 12, we're in section 4. So remember, the derivative of the chemical potential of A with respect to pressure holding temperature constant is just equal to the partial molar volume of A. And remember, A is our solvent. Now also we know from way back chapter 2, the differential of Gibbs free energy is equal to minus the entropy times the differential of temperature plus volume times the differential of pressure. We're going to be holding temperature constant, so this whole term goes to 0. So that would just give us dG is equal to VdP. Now we know the partial molar volume of A is going to be greater than 0. And we know that the change in the chemical potential of A is going to be greater than 0. Therefore, the derivative of pressure is going to be greater than 0. Now let P equal the equilibrium pressure on the left side, and P plus pi be the equilibrium pressure on the right side. That means pi is the extra pressure that we would apply to the right side in order to make the chemical potential of A on the left side equal to chemical potential of A on the right side. Now we call pi the osmotic pressure. And of course at equilibrium we know that the chemical potential of A on the left has to equal the chemical potential of A on the right. Continuing on physical chemistry, chapter 12, section 4, we're talking about osmotic pressure. So continuing that integral we did on the previous slide, the chemical potential of A in the pure state at pressure P plus pi and temperature T minus the chemical potential of A in the pure state at pressure P minus temperature T is equal to the molar volume of A in the pure state times the pressure plus pi minus the pressure. So simplifying those two out, we just get that the chemical potential of A in the pure state at pressure P plus pi and temperature T minus the chemical potential of pure A in the pure state at pressure P and temperature T is equal to the molar volume of A in the pure state times the osmotic pressure pi. That's a capital pi, by the way, in case you can't tell by my handwriting. So again, that's going to give us, we also know from before, whatever, chemical potential of A in the pure state at pressure P plus pi and temperature T is equal to minus the chemical potential of A in the pure state at pressure P and temperature T equals minus RT natural log of gamma of A, or solvent, times the mole fraction chi of A, or solvent. So, setting these two equal to each other by transitivity of equality, we can say minus RT, times the natural log of gamma A chi A is equal to molar volume of A star times the osmotic pressure. And now, solving for the osmotic pressure then, we have minus RT divided by the molar volume of pure A times the natural log of gamma A times the mole fraction chi of A. And this is going to be true for any solution. But if we think of an ideally dilute solution, we know that from a few slides ago, natural log of the gamma A chi A is roughly equal to minus the mole fraction of B. So we can just substitute that in and say that the osmotic pressure for an ideally dilute solution only is equal to RT divided by the molar volume of A in the pure state times the mole fraction of B. Notice how the double negatives cancel out. So this is basically assuming that gamma is equal to 1. So ideally dilute solution only. Continuing on physical chemistry, chapter 12, section 4. So we already showed this before in a previous section, but just to refresh your memory, we know that the mole fraction of B is equal to the number of moles of B divided by the total number of moles of A plus the number of B. This is for a two-component system. And if we're talking about an ideally dilute solution, where A is the solvent and B is the solute, then their Na is much larger than Nb. Therefore, the mole fraction of B is roughly equal to the number of moles of B divided by the number of moles of A. So we're going to substitute that back into the formula for pi here, and capital Pi, the osmotic pressure, and that's equal to RT over the molar volume of A in the pure state times the number of moles of B divided by the number of moles of A. Now we also know that in an ideally dilute solution, the total volume is roughly equal to the number of moles of A times the molar volume of pure A. So solving that for just the VMA star, we get the molar volume of pure A is equal to the total volume of the solution divided by the number of moles of A. Then we want to substitute that back into the formula down here, and we get the osmotic pressure pi is equal to RT over V over Na times NB over Na. Notice these two Na's cancel out. So we just get pi is equal to RT times the number of moles of B divided by the total volume of the solution. And then the number of moles of B in the solution divided by the volume of the solution is just the concentration, Cv. So we have pi is equal to the concentration of B in the solution times RT. So Cv is molar concentration. You might also see abbreviated capital M for molarity, but molarity is usually only referred to liquids. And, well, I guess we were talking about liquids, so you might see it as capital M there. And this is true, remember, because Cv, concentration is Nb over V. So now we just have pi is equal to CVRT, and this is called the Van Hoff law. Continuing on physical chemistry, chapter 12, section 4, more about osmotic pressure. Most of these time you're doing calculations, you'll want to do R as 0.08206 liter atmospheres per mole Kelvin instead of the normal 8.216 joules per mole Kelvin. So if you're talking about electrolysis, then we'll have pi is equal to I CVRT. So I is going to be equal to 1 for non-electrolyte, so it dropped off, and you have pi equals CVRT. But if you have an electrolyte, I is going to be greater than 1. This I is called the Van Hoff factor, because this is the Van Hoff law. So as an example, for calcium chloride, I is going to be equal to 3, because when this dissolves and dissociates into its ions, you're going to have 1 calcium 2 plus ion, and then 2 chloride ions, anions. So That would be just pi equals 3 CVRT. Now here's a graph. We're going to do pi divided by ATM to cancel out, make it useless here. So we have pressure, osmotic pressure, against concentration. Now based on the Van Hoff law, obviously we get a straight line like this. On the other hand, for a real solution, it's actually going to curve upwards. Remember all those different approximations we made about volume and so on. Continuing on physical chemistry, chapter 12, section 4, we're talking more about osmotic pressure. So let's say we have the similar system as before. On the left side we have pure water, on the right side we have some sort of aqueous solution, and in between we have a membrane that only passes water. Reverse osmosis is when we apply pressure here to the right side, the side of the solution, to get pure solvent out the left side. This is how water treatment is done on, countries like Saudi Arabia, where they have they're next to saltwater, ocean or lake or whatever. They got energy but no clean water, so they do this. So if you increase the pressure on the right side, what you're doing, of course, is you're making the chemical potential of the A on the right side greater than the chemical potential of pure A. Now in water, this takes about 600 to 900 pounds per square inch is how it's done. Now let's talk about inside a cell. It could be in your body, it doesn't matter. The cell is surrounded by fluids. It could be sap in the case of a tree or lymph, or it could be blood in the case of a mammal, whatever. So we're going to compare what happens, the osmotic pressure inside the cell versus the surrounding fluids. Okay, continuing on physical chemistry, chapter 12, we're finishing up section 4 now. We're finishing up talking about osmotic pressure. So we showed that if you have a cell within a surroundings fluid, such as blood, what's going to happen? Well, there are three possibilities. One is that the concentration in the surroundings is greater than the concentrations in the cell. So therefore, the osmotic pressure in the surroundings is greater than the osmotic pressure in the cell. So the fluids are going to leak out of the cell. So the surroundings are hypertonic. And the cell is going to shrivel up because fluids are leaking out. The second case is if the concentration of the surroundings is less than the concentrations in the cell. Then the pi in the surroundings, the osmotic pressure in the surroundings, is less than the osmotic pressure in the cell. We say then the surrounding is hypotonic. And the cell, because it's picking up all this fluid, is going to expand and it could eventually burst if there's enough fluid. And then the third choice, of course, is if the concentration in the surroundings is equal to the concentration in the cell. Therefore, the osmotic pressure in the surroundings is equal to the osmotic pressure in the cell. And we say that they are isotonic, which means they have the same osmotic pressure. Continuing on physical chemistry, chapter 12, we're beginning section 6 now. We're going to talk about two-component liquid-vapor equilibrium. Now, let's say we have two components, then the independent components, C equals 2. We're going to talk about, if we had P equals 1, just one phase, then F equals independent components, F is degrees of freedom, remember, minus the number of phases plus 2. So we get 2 minus 1 plus 2 equals 3. So that's the bare minimum. So if you wanted to do a phase diagram, you would have to graph temperature and pressure and mole fraction of one of the substances. That would be three-dimensional, and making a 3D diagram and understanding it can be hard to do. So instead what we're going to do is keep one of those three variables constant and just graph in 2 dimensions like we've been doing. So the first thing we're going to do is we'll talk about an ideal solution, and we'll just keep temperature fixed. So we're going to end up graphing pressure versus mole fraction of A. So we're going to say we have liquids A and B, volatile and volatile, which means they have vapor pressure. And we're going to have a temperature, any constant temperature, as long as it's greater than the freezing temperature of either A or B. Now the overall mole fraction in this system would be the total number of moles of A divided by the total number of moles. This is a closed system, of course. If we have an open system, can't really do this. So if we're going to be talking about liquid-vapor equilibrium, then the overall mole fraction of A is equal to the number of moles of A in the vapor phase plus the number of moles of A in the liquid phase, divided by the number of moles of A in the vapor phase, plus plus the number of moles of A in the liquid phase, plus the number of moles of B in the vapor phase, plus the number of moles of B in the liquid phase. Continuing on physical chemistry, chapter 12, section 6, we're talking about liquid-vapor equilibrium. So let's say we have a constant temperature bath, and in that we have a cylinder with liquid A and B, and is held down by a piston applying pressure P. Now we're going to raise up this piston to decrease the pressure in our system of A and B. And we're going to use this information to make a phase diagram. So let's say we start out at this mole fraction, and this higher pressure. Remember, we're going to decrease the pressure. So we start at C prime, we're going to decrease to D prime. Whatever pressure this may be, this is when we're going to start to vaporize. So from here down, we're going to have liquid and vapor phase in equilibrium. As we continue to decrease the pressure, we're going to get to pressure, this point F prime. So whatever pressure this is going to be, this is when the last of the liquid vaporizes. And then below this, all we have is gas. And we could do this for any concentration. Now, of course, with different concentrations, these points might be higher or lower. We don't have any numbers yet, but this will give you a rough idea of what's going to happen. So as I was just explaining, we're going to start at C prime, we're going to decrease the pressure, P, and then D prime is when the vapor first appears. Now below D prime, there's going to be vapor of both substances, but in the vapor phase, there will be a higher concentration of whichever substance is more volatile. Continuing on physical chemistry, chapter 12, section 6, we're talking more about liquid-vapor equilibrium. So remember the graph in the previous slide. So when we're at F prime is the last of the liquid. And so below F prime is all vapor. So at C prime, we know that the mole fraction of A is equal to the mole fraction of A in the liquid phase, because that's all there is, liquid phase. At D prime, when we just have the first little bit of vapor, then we can round and say that the mole fraction of A is roughly equal to the mole fraction of A in the liquid phase. But we're going to have to use Raoult's law for points farther down. So one, we know that the mole fraction of A in the vapor phase is equal to mole fraction of A in the liquid phase times the pressure of A pure divided by the total pressure. And doing the same thing for the other component, mole fraction of B in the vapor phase is equal to mole fraction of B in the liquid phase times the pressure of pure B divided by the total pressure. Now we're going to divide those two equations, and we're going to get the mole fraction of A in the vapor phase divided by the mole fraction of A or B in the vapor phase is equal to the mole fraction of A in the liquid phase divided by the mole fraction of B in the liquid phase times the pressure of pure A divided by the pressure of pure B. Notice the total pressures cancel out. So what this should tell you is if keeping the mole fraction of A of whatever in the liquid phase, then if we have a higher partial pressure of pure A, or a higher pressure of pure A than pressure B, then you'd expect a higher mole fraction of A in the vapor phase than the mole fraction of B in the vapor phase. Finishing up, chapter 12, this is the last of section 6. So here's another phase diagram, just like the one before, except that was pressure against mole fraction. This is temperature against mole fraction. So even though it's dipping down, we still call this positive deviation, because, on pressure, it bulges up. So anyway, so we have the boiling point of pure B and the boiling point of pure A, and then our azeotropic mixture is lower. So at higher temperatures, we have all vapor. Lower temperatures, we have all liquid. And then in between, we can have a range of liquid and vapor, except, of course, at the azeotropic mixture. And then we have just one actual boiling point, just like you would with a pure substance. So we're going to say that this XA prime, or chi A prime, that's our azeotropic mixture. Now remember, higher vapor pressure means lower boiling point. That's why on the previous slide, remember, we had the pressure of B star down here and the pressure of A star up here. So if it looks upside down, just make sure you're paying attention to temperature or pressure. So if the mole fraction that we're looking at is greater than the mole fraction of A prime, and we do fractional distillation, just think of your tie line. You're going to get pure A. Wait a minute. Wait. Hang on a second. Okay, continuing what we were talking about before. So we want to know what is the mathematical function describing points like D prime, D double prime, D triple prime, F double prime, F triple prime. In other words, where we have both liquid and vapor phase. Well, between D and F, we have the liquid and vapor phase. They're in equilibrium. So we want to derive an equation for the D points. Remember, this is at the top where there's just a little bit of gas forming. Everything else is liquid. Now we know that the mole fraction of B in the liquid phase is equal to 1 minus the mole fraction of A in the liquid phase. So using that, we're going to say, okay, the pressure in the solution has got to be equal to the pressure of A plus the pressure of B. The pressure of A is going to be equal to the mole fraction of A in the liquid times PA star. And then the pressure of B is going to be equal to the mole fraction of B in the liquid phase times PB star. So that's using this. We'll say, oh, and then simplifying, we're going to say, okay, the pressure is equal to PA star minus PB star times the mole fraction of A in the liquid plus PB star. So this is the formula we want. Notice that if we're going to graph pressure against mole fraction of A, we have slope y-intercept form. And that's good. So the mole fraction of A in the liquid phase, we're going to say is roughly equal to the mole fraction of A at point D prime, because this is when the first droplet is appearing. Continuing on physical chemistry, chapter 12, section 6. We're still talking about liquid-vapor equilibrium. So we found that formula for a line, slope y-intercept form. So here we are, we're going to graph pressure against mole fraction of A. So mole fraction goes all the way from 0 to 1. So we have one mole fraction we're calling XA prime, or chi A prime. Another one we're calling chi A double prime, and one we call chi A triple prime. So at higher pressure, it's going to be all liquid. At lower pressure, we're going to end up with any point where it goes to first little bit of gas. Let's see here. So we're starting out with the no A, we're going to have pressure just PB star. And with pure A, we're going to have pressure PA star. Now this shows PA star higher than PB star. That's arbitrary. You can switch them around and they'll still make a straight line, just be reversed. Now that we've done that, we want to solve an equation for the F points. So what we're going to do is we're going to take the same equation for the line, but we're going to use the mole fraction of A in the vapor phase is equal to mole fraction of A in the liquid phase times the pure pressure of A divided by total pressure. And we're going to solve that for the mole fraction of A in the liquid phase. So here we are, the mole fraction of A in the liquid phase is equal to the mole fraction of A in the vapor phase divided by the pure pressure of A divided by the total pressure. So we're going to substitute this back into the formula for that straight line there, like this. So we have total pressure is equal to the pressure of pure A minus the pressure of pure B times the mole fraction of A in the vapor phase divided by the pressure of A pure divided by total P plus PV star. Doing a little algebra on that, we get the pressure is equal to the pressure of A pure times the pressure of B pure divided by the pressure of B pure minus the pressure of A pure times the mole fraction of A in the vapor phase plus PA star. Now this is the formula for our F points now. Notice that this is not a line. Continuing what we had before, we just found the equation for our F lines. This is what they look like together. So we have our mole fraction of A down here and our pressure up here. We picked 3 points, mole fraction of A prime, mole fraction of A double prime, mole fraction of A triple prime. And we've got the pure B over here, so that's pressure PB star. Pure A over here, so that's pressure PA star. Connecting them, the top line, the D lines, that's supposed to be a straight line. Above that is only pure liquid. And then the other curve we just derived, those are the F lines. This one, it looks like it's curving down, but it doesn't go below. It's pretty, anyway. So below that is vapor, and in between you have liquid and vapor. So let's talk about the lever rule and tie line. Let's say we have the same graph up here. We have pressure over here, mole fraction of A on the bottom here, XA, and that's in the, that's total mole fraction. Okay, so we have our straight line up here, where we had labeled D points before, and the curve down here, F points. Now let's say we start at point C up here in the liquid phase, and we're going to decrease the pressure with the piston, just like we did before. Then we're going to keep on going down. This vertical line here, this is called an isopleth line. That means constant composition, because obviously it's whatever mole fraction here. Now what we want to do is figure out at point E, what do we have in the vapor phase, and what do we have in the liquid phase? This horizontal line here is called a tie line. So it goes from point E straight to the left until you hit the top curve. We're calling that point H. And you start at point E, go straight to the right until you hit the other curve. We're calling this point I. Continuing on physical chemistry, chapter 12, section 6. We're talking about liquid vapor equilibrium still. So here's the same graph we've been using before. We got pressure against mole fraction of A. Our pressure here, our point of interest here is E. We're somewhere in the liquid vapor region, and we want to know what the mole fraction is. So we create this horizontal line called the tie line. So go straight to the left, we get H. Let's go straight to the right, we got I. So when you're at point I here, this is going to tell you what the composition of the vapor phase at point E. And when you're at point H here, this is going to tell you the composition of the liquid phase for point E. Now, lowercase n sub A is the total number of moles of A. And that's in the liquid and vapor phase, remember, because it's in both. So NL, that's the total number of moles in the liquid phase. And that's A and B, or all components if there's more than two. Likewise, N sub V is going to be the total number of moles of A and B in the vapor phase. Now we know that the mole fraction of A, overall, for both phases, is just the number of moles of A and divided by the number of moles in the liquid plus the number of moles in the vapor phase. Because this is total moles, right? So we're going to say, okay, the number of moles of A, that's the mole fraction of A times the number of moles in the liquid phase, plus the mole fraction of A times the number of moles in the vapor phase. But that also gives us then the number of moles of A in the liquid phase, plus the number of moles of A in the vapor phase. That's all we're doing here, combining these two. And that's equal to the mole fraction of A in the liquid phase times the number of moles in the liquid phase, plus the mole fraction of A in the vapor phase times the number of moles in the vapor phase. So what that tells us is that the mole fraction of A in the liquid phase plus the mole fraction of A times the number of moles in the vapor phase has got to be equal to the mole fraction of A in the liquid phase times the number of moles in the liquid phase plus the mole fraction of A in the vapor phase times the mole fraction of N in the vapor phase. So just get those two, the liquids on the same side and the vapor on the other side. We have the mole fraction of A times the number of moles in the liquid phase minus the mole fraction of A in the liquid phase times the number of moles in the liquid phase. And that's equal to the mole fraction of A in the vapor phase times the number of moles in the vapor phase minus the mole fraction of A in the vapor phase, or total, times the number of moles in the vapor phase. Continuing on liquid gas or liquid vapor equilibrium. So factoring out the number of moles, then we get the number of moles in the liquid phase times the mole fraction of A minus the mole fraction of A in the liquid phase is equal to the number of moles in the vapor phase times the mole fraction of A in the vapor phase minus the mole fraction of A. Now remember from the graph I already drew, the distance then is going to be the distance from E to H is a bar over it. So this difference here is going to be equal to point E to H, and this difference here is going to be point E to I. So we have the number of moles in the liquid phase times the length of line segment EH equals the number of moles in the vapor phase times the length of segment EI. This is one form of the lever rule. Now let's say alpha and beta are phases, and then we're going to use lowercase l for the length in this example. So n of alpha times L alpha equals MB beta times L beta. This is another form of the Lever rule. So that's the number of moles of phase alpha times the length of that tie line, at the left side of the tie line, phase alpha, equals the number of moles of beta times the length of that tie line on the right side. Now this only applies to liquid-gas equilibrium. Now we could rewrite it instead of using mole fractions, or moles, using weight fractions. So we could put M alpha L alpha equals M beta L beta. And M is the weight fraction. Now, remember the straight line that we derived, those D points, that curve is called the bubble point line, because this is when you take the liquid and you first start gas bubbling. The bottom curve that we derived, that's called the dew point line, because that's what if you come the other direction when you have vapor, this is when you'll first get a drop of dew forming. This is physical chemistry. We're continuing chapter 12, section 6. We just finished talking about an ideal solution at constant temperature. Now we're going to talk about what happens if we have an ideal solution at constant pressure. So here's a graph of your mole fraction of A against temperature. Well, temperature versus mole fraction of A in a two-component system. With A and B are both liquids. But of course at lower temperature they're both going to be liquids. Higher temperature they're going to both be vapor. And then in a certain range of temperatures, depending on the mole fraction, you'll have both liquid and vapor in equilibrium. Now let's say here that you start with a certain mole fraction of A. We're going to call this the mole fraction of A in state 1. And you heat it up to this temperature here, so that gas just starts to form. So we just start getting a little bit of bubbling. Then the mole fraction of the liquid is going to be whatever we had here on this line that we started with, the mole fraction of A at state 1. But if you follow this horizontal line across all the way to this other curve, then that'll tell you the composition of the vapor that is coming off. So we're going to call that the mole fraction of A in state 2. Now likewise, if you condense that to liquid and then boil it off, you come up to this line here when you first get a little bit of gas, vapor, and you go straight across to this other curve, and this will tell you the composition of the vapor that's coming off that second distillation, just coming down to the mole fraction of A in state 3. So you just keep repeating this step, and of course it'll get smaller and smaller as you get in here. But this is how you separate A from B. This is called distillation. Each step here is actually distillation. When you do it over and over like this, it's called fractional distillation. So one thing to keep in mind though, we're comparing two different liquids here, B and A. Notice B here has a higher boiling point. Therefore, it's going to have a lower vapor pressure. Okay, physical chemistry, chapter 12, section 6. We're continuing about the liquid-vapor equilibrium in a constant pressure system. Now remember that graph on the previous slide and how we had those horizontal lines? So now we're talking about theoretical plates. Each one of those horizontal lines on that phase diagram on the previous slide is one theoretical plate. That theoretical plate is the maximum degree of enrichment you're going to get if you distill it just one time, or one step in a multi-step distillation process. One way you can do that is if you have a fractionating column, you could just put beads in it, or something else that'll basically increase the surface area, because then you'll continually, boil off, condense, boil off, condense. Obviously, if you do more and more of those steps, more of those theoretical plates, you're going to get better separation. Now, this is especially important if you have two liquids that have boiling points that are close together. You might need a whole bunch of theoretical plates to separate them. Like, let's say you wanted to get heptane from octane or something like that. It's very similar molecules. And oil refineries do this all the time. They've got these big refinery columns, or fractionating columns, that they might have thousands of theoretical plates, and they could be, really tall cylinders. You've probably seen them. Continuing physical chemistry, chapter 12, section 6. Now we're talking about non-ideal solutions. Now, before we talk about what non-ideal solutions really do, we're going to use an example of what a non-ideal solution cannot do. This is an example of phase diagram that has to be wrong. It's pressure versus mole fraction of A holding temperature constant. So we have at higher pressure, all liquid, at the lower pressure all vapor, and then in between here there'd be liquid and vapor in equilibrium. Now let's say that you are on this mole fraction here, and you come down to point D. So you're lowering the pressure. Now according to this curve, it's going to start vaporizing. You're going to get some gas. But to find the mole fraction of A in the gas, you'd have to use the horizontal tie line over to the vapor curve to find out what is the composition of the gas. As you can see for point D, it's on the liquid curve only. There is no vapor composition curve. So what that tells us is that, at least for point D, this diagram doesn't make any sense. Likewise, if you go farther down here, same thing. If you go left to this tie line, right to this tie line, it's giving you two different liquid compositions, but it's not telling you the vapor composition. So this diagram just absolutely makes no sense. So this is what phase diagram can look like for liquid vapor equilibrium for a real gas, right? Well, liquid gas equilibrium. Now this is a constant temperature, so we have pressure against mole fraction of A, with the other component being B, but it doesn't matter. So up above a certain temperature or pressure, we have just pure liquid. Down at lower pressure, we have pure vapor. And then in between, we can have liquid and vapor in equilibrium. Now what's important then is that anywhere within here you pick a point, you draw your tie lines, and you can get the composition of the liquid and composition of the vapor. This is why this kind of diagram can work, as opposed to the one on the previous slide that was impossible. And even on the right side over here, you draw your tie line and you get to the liquid curve and the vapor curve. Now there is one composition here called the azeotropic composition. I'll get to that in a minute. So the way it bulges up like this is called positive deviation. I'll show you on the next slide what negative deviation looks like. So this whole top curve here, arching over, this is called the liquid curve. And then both of these curves down here, this is called the vapor curve. So this dashed line here, where it goes to this point, this is called the azeotrope, the azeotropic composition. It's a certain mole fraction. So this is also known as a constant boiling mixture, because with this composition, you're going to boil off at one certain pressure, one certain temperature, as opposed to any other composition where you have a whole range of pressure to boil off of. Now one example, of course, would be ethyl alcohol, 96% ethyl alcohol and 4% water. This is why if you're making vodka or whatever, you can't make 200 proof alcohol just by distillation. Finishing up, chapter 12, this is the last of section 6. So here's another phase diagram, just like the one before, except that was pressure against mole fraction. This is temperature against mole fraction. So even though it's dipping down, we still call this positive deviation, because, on pressure, it bulges up. So anyway, so we have the boiling point of pure B and the boiling point of pure A, and then our azeotropic mixture is lower. So at higher temperatures, we have all vapor. Lower temperatures, we have all liquid. And then in between, we can have a range of liquid and vapor, except, of course, at the azeotropic mixture. And then we have just one actual boiling point, just like you would with a pure substance. So we're going to say that this XA prime, or chi A prime, that's our azeotropic mixture. Now remember, higher vapor pressure means lower boiling point. That's why on the previous slide, remember, we had the pressure of B star down here and the pressure of A star up here. So if it looks upside down, just make sure you're paying attention to temperature or pressure. So if the mole fraction that we're looking at is greater than the mole fraction of A prime, and we do fractional distillation, just think of your tie line. You're going to get pure A. Wait a minute. Wait. Hang on a second. Okay, this is Physical Chemistry, Chapter 12. We're finishing up Section 6 now. So here we are. We've got a phase diagram again. This time we're holding constant, or pressure constant. So we're graphing temperature against mole fraction of A. We're still doing positive deviation. Now remember, before we had pressure versus mole fraction. So the pressure of B star was down here, and the pressure of A star was up here. With temperature, it's going to be reversed. Now this mole fraction here XA prime, that's our azeotropic mixture. Now, if our, let's see. Okay, so if our mole fraction here is greater than XA prime, we're in here and we do fractional distillation. Well, one theoretical plate is going to give you this much, but if you keep distilling, what you're going to end up with is pure A and then your azeotropic mixture. Now, if your mole fraction that you start out with is over here, left of the XA prime, then and you do fractional distillation, well, remember, one theoretical plate will do this, but then you keep spreading out those and those and those, and eventually what you're going to end up with is pure B and your azeotropic mixture. Now, you can actually change the pressure though, and that will change the position of your azeotropic mixture. We're in Physical Chemistry, Chapter 12. We are now beginning Section 7. Section 7, we're going to be talking about two component systems that are in liquid equilibrium. So we're going to have to talk about a couple of definitions of what can happen when you mix two liquids. One is that they're miscible. Miscible is when two liquids are completely soluble in each other. Now that means any mole fraction, right? You can have 0 to 1 or anywhere in between, and they'll totally dissolve each other. So what this means is you're going to have a single phase. All the liquid phase is one phase. One example would be water and acetone. Those two will dissolve each other in any mole fraction. Now this is also, by the way, why adding acetone will actually dry out a container. Because you add the acetone, the water dissolves in the acetone, but acetone, it has low vapor pressure, so it evaporates, and it takes the water with it. Now other examples would be if you have a low molecular weight alcohol like ethanol or methanol. Now partially miscible means two liquids are going to be partially soluble in each other. One example would be like pentanol and water. Pentanol, as you know, is a chain hydrocarbon, but then it's got the alcohol group at the end. The alcohol group is hygroscopic, so it'll hydrogen bond to the water, but the chain there is hydrophobic. It's not, except for, induced dipole, is not really going to bond. So pentanol and water, they'll dissolve, but only in certain mole fractions. Continuing on Physical Chemistry, Chapter 12, we're in Section 7 now. So I mentioned before how pentanol and water, they're partially miscible, which means they, in certain mole fractions, they might not totally dissolve in each other. Here's a phase diagram showing those two. So here's temperature versus mole fraction of one or the other. I mean, without these numbers, it doesn't matter which is which. So at really high temperatures, you're going to have only one phase. They'll be completely soluble in each other, or completely miscible. At lower temperatures, though, if you have a really low amount of one, it'll all be one phase. If you have a really low amount of the other, it'll all be one phase. But if you have a significant amount of both, then you're going to have two different liquid phases. And if you have two or more liquid phases, or well, two or more of any phases, then you can use the lever rule to do your calculations and find out what's going on. And the lever rule, it applies anytime you have two substances in equilibrium. Now this temperature up here, this highest temperature where you can have two phases, this you might call the critical solution temperature, or just TC. This is where the two phases here become one. So TC in this case is our upper critical temperature. Continuing on Physical Chemistry, Chapter 12, Section 7, we're talking about liquid-liquid phase equilibrium, different things that can happen. Here's an example of water and tertiary amine. So you'll notice here that at any mole fraction, at low temperatures, we're going to have only one phase, in this case below 20 degrees Celsius. But at higher temperatures, you'll have two different phases. Now these are both liquid phases. So that just means, remember, down here they're miscible or completely soluble, and up here they're partially miscible. And notice over here that the mole fraction, the temperature goes up. So there are mole fractions in here where it is higher than 20 degrees Celsius. This horizontal temperature here, 20 degrees Celsius, the lowest temperature where you can have two phases, that's our critical temperature. In this case, it's the lower critical temperature. Continuing on Physical Chemistry, Chapter 12. This is the last of Chapter 7. So now we've got a situation in which the two liquids that are partially miscible. Notice this is temperature against mole fraction of whichever. So you notice that really low composite, when one's almost pure, you get one phase. When one's almost pure, you get one phase. At really low temperature, you get one phase. At really high temperature, you get one phase. But if you have a little of each and a certain range of temperatures, you're going to have two phases, which means they're not, well, they're only partially miscible. You've got two phases. The higher point here, where you can have two phases, this is a critical point, so this would be your upper critical point. And likewise, the lowest temperature, where you can have two phases, this is another critical point. This is your lower critical point. Now, this particular example happens to be nicotine and water, even though I forgot to label which temperatures exactly. But helium and neon, or helium and xenon would do this, ammonia and methane would do this, or carbon dioxide and water would do this. Now, this whole two-phase region in here, this is called the miscibility gap. Now, this upper temperature, the upper TC, critical temperature, that's actually caused by entropy. When the temperature is so high, you get TDS is greater than delta H. Continuing on physical chemistry, chapter 12, we are in section 8 now. Now we're going to talk about if we have two components and we have both the solid and liquid phase in equilibrium. Now, in the first example, we're going to say the A and B are miscible in all proportions in the liquid phase, but completely immiscible in the solid phase. Now remember, this is temperature against mole fraction of A, so we're going to hold pressure constant. So, let's see here, start at the top. So at higher temperatures, it's going to be liquid solution. Everything's going to be in together. They're completely miscible, so there's only one liquid phase. At really cold temperatures, you're going to have solids. Now we said they're completely immiscible, therefore you're going to have pure solid A and pure solid B. However, let's say you're in this region here. Well, you got to draw the tie line, and you're going to say, okay, we've got pure B and liquid solution. And likewise, if you're anywhere in here, you draw the tie lines, and you see, okay, I got liquid solution and pure A. Now, let's see here. Okay, and then of course, the TB star, remember, this is the melting point of pure B. And then over here, this would be the melting point of pure A. Continuing on physical chemistry, chapter 12, section 8, we're still talking about when we have two components in liquid and solid phases, and they're completely miscible in the liquid phase, but completely immiscible in the solid phase. So this is the same diagram as before. I redrew it a little bit smaller so we can add some stuff here. So this top curve here, going from the normal boiling point down here, this is actually the freezing point depression of B caused by adding A. And likewise, this other solid, this curve up here, this is the freezing point depression curve of A due to adding B. Because remember, this is mole fraction of A on the horizontal axis. Now, let's say that we start in this system here, the liquid solution, higher temperature, and we allow it to cool until you're down to T1. Remember, you draw your tie line, and you know that pure B is going to freeze out. Now you lower the temperature some more down to T2, and again you draw your tie lines, you still got liquid solution, and you got pure B freezing out. Then when you come all the way down to T3, this is when everything's going to freeze. You're going to have pure B, and you follow the tie line all the way over here, you're going to get pure B, or pure A also. And then if you're anywhere inside of here, like at where I showed you T2, then you can use the lever rule to do your calculations. Continue on physical chemistry, chapter 12, section 8. We're still talking about the same diagram as the previous two slides. This point down here at the bottom of these two melting curves, we're calling that point E. E is the eutectic point. And eutectic means easily melted, and this is the minimum melting point. Continuing on physical chemistry, chapter 12, section 8. Now we're going to talk about solid solutions. And substance A and substance B mix, and they can form a solid solution at the atomic or molecular level if they have these three properties. One is that they have similar chemical properties. Two is that they have similar crystal structure. And three, they have an appropriate radius ratio. I'll show you on the next slide what that means. Now, upon cooling these solid solutions, they can either have 1, complete miscibility, 2, partial miscibility, or 3, complete immiscibility. And of course, these will have different phase diagrams. Coming up, here's physical chemistry again, chapter 12, we're still in section 8. So we talked on the previous slide about how a solid solution, the atoms or molecules must have an appropriate radius ratio. Now, what that means depends on the type of solution. One is what we call an interstitial solid solution. Notice here we have these huge atoms lined out nice and neatly in whatever crystal structure they have. And then in between we got these smaller atoms squeezed in between. Now in this example, the big atoms are iron and the small atoms are carbon. This is called steel. And other examples would be zinc and copper, that's called brass, or titanium and hydrogen, that's called titanium hydride. Now the other alternative would be the more obvious one, substitutional solid solution. Notice we have all these different atoms lined out in whatever crystal structure, and they're all almost exactly the same size, but you have these solid ones and these dashed ones. So in this case, the solid one is nickel and the dashed one is copper. Notice they have almost the exact same radius. The radius of nickel is about 125 picometers, and then the radius of copper is about 128 picometers. So the coin that we call a nickel is obviously not pure nickel. So at 25% weight nickel and 75% weight copper. This makes it harder than either pure nickel or pure copper, and more corrosion resistant than either pure nickel or pure copper. Continuing on physical chemistry, chapter 12, section 8. So now we're talking about what if, you have two components and they're miscible in both the liquid phase and the solid phase. Okay, so we're going to hold pressure constant. We're going to have temperature against mole fraction of nickel. So we have pure copper over here, pure nickel over here. So at higher temperatures, it's going to be melted, obviously. So this is a liquid solution at any mole fraction. Likewise, at low temperature, they're going to be totally solid, one phase, a solid solution at any mole fraction. Excuse me, in between, of course, at any mole fraction, except for pure substances at the end, you're going to have both liquid solution and solid solution. So if you come up here, you go to this point, your solid solution is going to be this mole fraction, and your liquid solution is going to be this mole fraction, because this horizontal dotted line, that's your tie line, just like we did before. It's the same of every two-component phase diagram. Now this top curve here, this is called your freezing point curve, or just your freezing curve. And this bottom line here, or curve actually, that's called your melting point curve. So if you're starting your liquid solution and you cool it down, the very first solid that's going to come out is going to be an alloy, but it's going to be richer in nickel. This is because out of the two, nickel has the higher melting point. Continuing on physical chemistry, chapter 12, section 8. Same diagram as the past few slides. So, let's see. If you take start up here, you go down here, it starts to freeze out. When you get down here to your freezing curve, this solid solution is going to have the exact same composition that your original solution did. Now remember, from your colligative properties, normally when you add an impurity, it causes freezing point depression, but in this case, it actually it rises instead. Notice, here's your freezing point of pure copper. When you add a little bit of nickel, your freezing point actually goes up. So this is an exception to that rule. Continuing on physical chemistry, chapter 12, section 8. Now, what if we have a solution that's not ideal? We're still talking about liquids and solids completely miscible in each other. So let's say we have copper versus gold. So at low temperatures, you'll have a solid solution. At high temperatures, you'll have a liquid solution. And then in between, you still got your tie line. So you'll figure out the mole fraction of your liquid solution, the mole fraction of the solid solution. So you notice here there's a minimum melting temperature. So this is what we call a minimum melting mixture. And likewise, here we have two different optical isomers of carboxene, the dextro and the levo one. So again, down at cold temperature, you'll have the solid solution. Higher temperature, you'll have your liquid solution, which is the same thing as a melt, by the way. And then in between, you're going to have your tie lines, where you figure out the composition of your solid solution, composition of your liquid solution. And then, of course, since this bulges upward, this will be a maximum melting mixture. Continuing on physical chemistry, chapter 12, section 8. We're still doing phase diagrams. We've got a lot more phase diagrams to talk about. So let's say that we have two substances. We're going to use silver and copper in this example. And they're completely miscible in the liquid phase, but they're only partially miscible in the solid phase. So that we're going to graph temperature versus mole fraction of copper here. So what's going to happen, of course, is at high temperatures, it's going to be liquid. Since they're completely miscible, we'll have one liquid phase, we'll have a liquid solution. Now at lower temperatures, what we're going to have is going to depend on how much copper or silver we have. Over here we'll have pure silver. Over here we'll have pure copper. In between, what we're going to actually have is called alpha and beta. Alpha is basically solid silver saturated with copper, and beta is solid copper saturated with silver. So as we heat it up, let's say we go up this way, we'll use your tie lines and you'll see, oops, I should have written, this is solid. This is solid. Okay. So let's say we heat it up here, we'll go through just solid alpha, which is just silver with copper. And then eventually, we'll get into a region where we have liquid and solid together. So use your tie lines, you'll see you have solid alpha and liquid solution. And eventually you get to the point where you have just liquid solution. Same thing over here. If you go up here, you'll start out with solid alpha and beta. With higher temperatures, you get more solubility up to a point, so you'll have just solid beta. So notice how the mole fraction of whatever can be considered alpha beta changes with temperature. And then, of course, eventually you'll get some melting. So just if you're anywhere in the diagram, just build your tie line horizontal and you can see what it's made of. And then we have a eutectic point right here at the bottom of this V. Let's see, what did I miss? And like I said, this is a case where silver and copper, the liquids are completely miscible. Silver solid and copper solid are partially miscible. Continuing on the previous slide, what we're talking about, a system in which you have total liquid miscibility, but only partial solid miscibility. How the phase diagram looks depends on exactly how soluble the two solids are. These three phase diagrams here, these are actually similar systems where you have complete liquid miscibility, but partial phase miscibility, but it's in decreasing miscibility in the solid phase. For example, this one here, notice you have a huge range in which you have only one solid, which means that the two substances are completely miscible. But you have a small miscibility gap, which is where the two solids are not, they're only partially dissolved in each other. You have your phase alpha and phase beta. And then remember up here, I showed it on the previous slide, I forgot to mention it. This loop up here is your solid liquid phase transition loop. So over here, it's the exact same thing, but the two solids, they're less soluble in each other. So your miscibility gap has grown. Notice it's gotten closer to your phase transition loop. And if they get even less soluble in each other, then what you have here is like on the previous slide, where the solid liquid phase transition loop intersects with the miscibility gap. So you have a huge range here with two solids, just a little bit, this is one solid, your alpha and beta. And then you have your solid liquid phase transition loop here. Continuing on with phase diagrams, now we've got one, again we're doing temperature versus mole fraction of A, and we've got a little different situation up here. So at high temperature we have melt, at lower temperature we have solid phase partial miscibility, so we have alpha over here, beta over here, and both in here. And then we have our solid liquid phase loop up here, but you notice how they overlap here. So let's say you start at point F. So what you have is solid alpha, which would be, B saturated with A, and then you heat it up to G. Follow your tie line, and you notice it's going to start melting at this composition. You heat it up some more, you're going to have, this alpha still, and then more melt at this composition. But then you get to H, and you notice what's going to happen. You're going to get beta and melt. So when you get to this part right here, your alpha is going to turn into beta. This is called your peritectic temperature, T sub P. Let's see here. So remember when you had a eutectic point, you had two different solids, and then when you heated them up, they became liquid. At a peritectic point, you have your solid. Well, actually, you have liquid in there too, but if you heat up this solid, and it becomes a different solid and liquid. So far we've been talking about situations in which we have two components. They're liquid phase miscible and solid phase immiscible. But now what happens if they form a compound? Now in this example we have phenol and aniline, and those two will form a compound of one of each, like PA. We're going to abbreviate it to PA. So this makes the diagram a little more complicated. So over here we have pure phenol, and notice up here you have liquid solution. This is the freezing point depression of the phenol due to adding aniline. Likewise, you start over here, you have pure aniline. Up here is liquid. This is the freezing point depression of the aniline due to adding phenol. And then if you keep going below that, you're going to end up with two solids. They're immiscible. You're going to end up with the solid phenol and then a compound. Notice your tie line only goes halfway across now. This is your compound, PA. Notice if you have just exactly a mole fraction of 0.5, this PA is going to go straight from solid to liquid. So it's going to do what we call congruent melting. Congruent melting means melting at one temperature. This line here is deliberate then. Even though on both sides you have liquid solution and you have your solid PA. Let's see here. Yeah, but like I said, any of these, you just draw your tie line and you can figure out what you have. And this is the same diagram as the previous phase where we have phenol versus aniline. One thing you'll notice though, now we have two eutectic points. We have one down here and one down here. Now that's good because for all the number of compounds you're going to have, call that N. Then you're going to have N plus 1 eutectic points. We have one compound, therefore N plus 1 is 2. We have two eutectic points. But that's assuming that there's no peritectic points. Okay, this is another example of what happens if you have compound formation when you have liquid phase miscibility and solid phase partial miscibility, or complete immiscibility. Now, the previous slide we had a 1-to-1 compound of AB. Now we've got a 2-to-1 compound of A2B. It looks about the same now. You still at high temperatures you have liquid solution. At low temperatures you've got two different solids, either B solid and A2B solid, or A solid and A2B solid. So over here, notice you have a eutectic point. So B and A2B becomes B in liquid solution, or B and A2B becomes A2B in liquid solution. But you notice up here, you've got a peritectic point. So let's say you take some A2B at just the right mole fraction here. This time you're not going to have congruent melting. Instead, what you're going to do is the A2B is going to turn into just pure A in liquid solution. Same thing if you have a little bit less, you'll have your B, solid B and A2B. Then you'll end up with A2B solid in liquid solution. And then eventually, this A2B will turn into just pure A solid in liquid solution. So this whole range in here, this is where or actually no, the whole thing here. This whole horizontal line is where you're going to go through a peritectic transition. Okay, just like on the previous slide, here we have a compound formation where we have liquid phase miscibility and solid phase immiscibility, but instead of having a 1-to-1 compound of AB, we've got a 2-to-1 compound of A2B. It's still the same though. We have liquid solution up here, and then we have solids down here. We have B solid and A2B solid here, or A solid and A2B solid here. And then if you heat this up, well, we've got a eutectic point here. So if you have just this mole fraction, you'll get your melt at a single temperature. So over here, you'll get B solid to A2B solid. Here, it'll turn into B solid to liquid solution. So just draw your tie line to see what that's made of. But over here, it's going to be a little bit different. Let's say you have the pure compound, A2B. When you get up to point M, it's going to go through a eutectic or a peritectic transition. So the A2B is going to turn into A solid in liquid solution. That's true over here too. If you start out here, you've got A2B and a solid in the liquid solution, and then you get to this temperature, the A2B is going to turn into A solid and different liquid solution. So anywhere in here, you're going to have a peritectic point. Okay, now that we've done a whole bunch of phase diagrams for 2-component systems, we can talk about a 3-component system. 3-component systems are known as ternary systems. Now the degrees of freedom, if we have just one phase, we're going to have 3 components minus 1 phase plus 2 is equal to 4. Now all our intensive variables, we would have like temperature, pressure, mole fraction A, mole fraction B, mole fraction C, etc. But remember, 2 of these 3 are independent because the third one has to make it add up to 1. So what we're going to do is we're going to keep temperature and pressure constant so that we can do all 3 of these mole fractions, which would be 2 degrees of freedom left, on one diagram, a 2-dimensional diagram. Otherwise, we'd have to graph it in 4 dimensions. So what we're going to do, we're going to make an equilateral triangle. Let's say we have substance A, B, and C. Then what we can do for any point inside D, we draw the line segment that's perpendicular here, call that E. Draw the line segment so it's perpendicular to this, call that G. Draw the line segment so it's perpendicular here, call that F. Now, we know that adding this plus this plus this is equal to the overall H, lowercase h, the height of the triangle. What we're going to do for the sake of convenience is just set H equal to 1. That way these 3 are going to add up to 1. So we know this segment here, DE, the length of this segment, is equal to the mole fraction of A. And then we know this segment here, DF, this is equal to the mole fraction of B. And then this line segment here, DG, this is equal to the mole fraction of C. And of course, by setting this H equal to 1, we get XA plus XA, XB plus XC, or chi A plus chi B plus chi C is equal to 1, which is what you would expect. Continuing on physical chemistry, chapter 12, we are in section 12 now. We're going to talk about 3-component systems. A 3-component system is known as a ternary system. Now the degrees of freedom formula, we have 3 components minus 1 phase plus 2 is equal to 4. So even if they're all in one phase, out of all these variables, temperature, pressure, mole fraction A, mole fraction B, etc., we have to use 4 of those to completely describe our system. Now what we're going to do is we're going to keep temperature and pressure constant so that we can graph all 3 mole fractions on the same diagram. That way we can draw a 2-dimensional diagram instead of having to figure out how to do a 4-dimensional diagram. So we're going to make an equilateral triangle. We're going to have component A, B, and C. And then we want to be able to describe at any point D within the triangle. So what we have here is we draw a vertical line or a perpendicular line to this segment, call this point G. Draw a perpendicular line to this side, call that point F. And draw a perpendicular line segment to D from this line segment, call it point E. Now what we want to do, or while we know that the length of this segment plus the length of this segment plus the length of this segment is going to be the overall height of the triangle. And for reasons of convenience, we're going to say that H is equal to 1. So now we know that the mole fraction of A here is going to be equal to the length of this segment DE here, because it's opposite. And then we know the mole fraction of B is going to be equal to the length of this segment here, because it's opposite. And then the mole fraction of C is going to be equal to the length of this segment here, because it's opposite. And since we said that the H of 1, well, we know mole fraction of A plus mole fraction of B, mole fraction of C equals 1. So now we know this plus this equals 1. That's why we were able to make these substitutions. Continuing on ternary systems, where we have liquid-liquid equilibrium, now we have a specific example of acetone, water, and ether. These are our three components. Now, acetone and water, as you can see, are highly soluble in each other, because at any mole fraction you're going to have only one phase. Acetone and ether, as you can see, are highly soluble in each other, because at any mole fraction they're going to have only one phase. But ether and water, as you can see, they're going to have they're not entirely soluble in each other, they're partially soluble. Because if you have a little bit of each, you're going to have two phases alpha and beta. Now remember I said before, we're keeping temperature and pressure constant on this kind of diagram. So in this case the temperature is 30 degrees Celsius and the pressure is 1 atm. And then in here we have alpha and beta, this is your one phase region. These diagonal lines, these are tie lines. Notice in this type of diagram, the tie lines are not horizontal lines anymore. They're a different angle. But as long as you still have two phases, you can still use the lever rule to do your calculations to find out how much of each substance you have. You just have to use the number of moles in phase alpha times the mole fraction of B minus the mole fraction of B in alpha equals the number of moles in beta times the mole fraction of B in beta minus the total moles of B. Okay, continuing on chapter 12. Actually, this is the very end of chapter 12. So we're talking about three component diagrams here. So we drew acetone, water, and ether, just like on the previous slide. Most of this out here is a one-phase region where the stuff is completely miscible. But in here we have two phases where they're partially miscible. So let's say that we have this point G here somewhere in the two-phase region. We draw the tie lines. So at one end we have point F and point H. And then you notice how the tie lines get shorter and shorter and shorter. So there's a point K out here somewhere where the length of the tie line is equal to 0. We say K here is the isothermal critical point, because remember this whole diagram is at constant pressure and temperature. And then, like I said on the previous slide with the lever rule, we have the number of moles in phase alpha times Fg is equal to, or times the length of Fg is equal to the number of moles in phase beta times the length of that segment GH.